Hello, welcome to ZenView Studios Lab, Eric speaking. Here, this is a new episode, this time about LCR meter, this one, tweezer type, which has some very good press, was compared by many to other bridge meters, real LCRs meters with very good comparison. And so I got one and I wanted to check how it compares to a multimeter that I have and how good the measures are. So let's dive in and see the actual measurements. All right, to complement a little bit what we're going to see afterwards, is the schematic of what I will show for comparison in terms of measuring ESR. You have a generator, which I will show you, set at 100 kilohertz with 500 millivolt square wave RMS. It's a 50 ohm generator, so we know that. And we will measure the V, which I call VESR, the change of voltage compared to the open circuit voltage and the loaded circuit voltage with the capacitor. And here is the formula that we use. The voltages are chosen so that we get a factor of 10 for the RESR. We read just by reading in millivolts this value, meaning if you have 11 millivolts, it's really 1 ohm ESR, 1.1 ohm ESR that you get from this formula. And that's the nice thing about this, is about why I chose 500 millivolts. Here's the explanation. Don't forget that if you read millivolts, you divide by 1000 to get volts. And that's it. Here's the example that I have in the video where 11.1 millivolts are measured and really gives a 1.13 ohm. That's for the ESR. Now, as far as the capacitance goes, it's the same generator. This time it's a 10 volt peak to peak at 10 Hertz, always 50 ohm output impedance. And we use 82 ohm, 82 point something ohm that we will measure. And we measure, in fact, the voltage across the capacitor here. And what we do is that we try to get the slope, the 63.2 voltage variation from 1 to V2. It can be anywhere on the linear part of the curve. I use, I think, 632 volts, 0 to 632 volts, something like that, to make the measurement. I get a time measurement, which is here, which is the angle. It measures the angle of the slope, and it's 7.45 millisecond in my example, and the calculation goes here. It's taken from the formula C equals tau over R, and you have 7.45 divided by milliseconds, 1000, divided by 82, and that gives 90.854 microfarad. And that's how we get to measuring the capacitance with just a simple generator. The precision is all in the cursor measurement that you do here. The more precise you get a measurement here, the more precise you'll get a value. Voila. Lastly but not least, the concept behind here is that when you have a test equipment, you should always be aware of how it functions. One thing we will see in the video is how this an ESR meter functions in some short way, and that's really where I point this, is that you always have to know that you have your test equipment, and you can use it in some other ways to figure out if some other piece is correct or not, and compare results between measures and instruments. That's the safe practice that you have to do. So here we are. So when it's turned on, that's the way it appears. You have push buttons that allow you, for instance, to change the voltage 0.3 volts so that you won't interfere with in-circuit measurements. 0.6 volt. This is the old button. If you kept it pressed, it will go back to 0.6, and the frequency at which it tests 100 Hertz, 1K and 100K, and 10K, sorry. You will see, and I will show you that in fact, even though it says 10K, the measurements that you get for ESR are comparable to the ones you would get with other test equipment at 100K. That's the interesting part. So we'll see that, and we'll see, the first thing we'll see is how precise is this gadget, because okay, we're supposed to have quite good precision. Right now it's milliohms with the tweezers pushed, and let's see, we can compare to some resistors that I have here on the bench. So we can compare it to resistors that we have on the bench here. Let's put it here and let's measure. So if you see, we get 8229, okay, 8228, 27, okay, and now let's have a look. I'll switch to something different. Let's have a look at what this meter says for the same resistance. Not bad, 355, 36, 37. So that's a 5.5 digit meter. So we can say it's quite good. So the first thing you have to notice is that this is also true, by the way. And I will show you again the meter. So this is also true if you measure in capacitance mode ESR. Because if you have, you can see here the value that's shown, 82.2928 for ESR value. What I'm saying is that one way to check an ESR meter is just to put a resistor. It's the simplest, there's no capacitance obviously, but it should read the proper resistance that you have, including milliohm resistance, I mean very small resistance. Here's just to show that 82, 26, 27, that's what the 5.5 digit meter showed, and that's very good. So that's a very simple way, if you have a better multimeter, to check whether this thing is accurate or not, and it is. So that's a very good point. The second way to do that is then to use another way of testing your ESR, and that's what we will do now. So now we're all set. Let's have a look at a little trick that we can play. With this in capacitor mode, we can check the ESR from this capacitor. At 1K it says 2.4 ohm. Let's put it at 10K. At 10K it says 1 ohm. Okay? I will show you now that you get exactly the same value, but it's at 100K. So this is the interesting part. Let me zoom first. So we can have a closer look at what I was measuring. Let's see if you can see what I was trying to show. Okay. Again, 1 ohm. This is what the ESR reads, 4.1 micro, and it's 1 ohm. And that's at 10K. Okay, now, to show you how I do it, I have a generator, the multimeter in AC mode, measuring 500 millivolt AC, because it's a 50 ohm output generator, and the scope, which says the same thing. Here it says 102 kilohertz, 534 millivolts. Maybe we can see that a little bit better. Let's see. And let's zoom in a bit. I don't know if you can see. Well, let's see. It's coming closer. Okay, so you see here they don't agree exactly on the RMS value, but it's close enough. The judge is really the 5.5 digit multimeter, which is here, which says 506 millivolts RMS. So what we will do is we will put the capacitor right here. So in between the generator and the ground. Up. And now let's look back at our multimeter. So there's a 10 decimal that you have to add, but it reads directly in ohm. So it's 1.115 ohm. That's what it reads exactly. The calculation is fairly simple because you have 50 ohm here, 500 millivolts RMS, and it's down to 11 millivolts here. If you run that by the voltage divider that it's making, you get that this reads really 1.16 ohm. So pretty close to that 1 ohm 8 or something that we read with the ESR meter. So that's another way to check that the ESR under real condition shows the same thing. So again, if I take off my capacitor from here and I put it there, in fact now it's reading 1.16, 1.15. So they agree very closely. You see, this is exactly the same value. And what I'm using for frequency, it's 100K. And this is shown also here. You can have a look. 100K and not 10K. As opposed to what's here on the dial. Oops, sorry if you can't see. I hope it will focus. Maybe not. So, okay, let's see a little further. Voilà. So I don't know if you can see properly or not, but it says actually 10K. So what I measured and showed is that we get an extremely good correlation between this and a 5.5 digit RMS multimeter that measure up to 200K or so with no problem, feeding a 100K signal. So that's really what's also very interesting, is that even though it says 10K, the measurement is close to what you'd get from 100K measurement with maybe some other LCR meter. So this is, the pulse is repeating at 10K, but the measurement is really closer to what you'd get at 100K. Why do I say that? Because if you measure the same capacitor with a different frequency, you will get a different ESR measurement, obviously. Oops, that's the wrong one. It's this capacitor. Okay, voila. So here now it's, you see it's moved a bit. It's 1.2, 1.19, ESR 1.16. Okay, this is at 10K dialed. But if I switch the frequency to, let's say, 100 Hertz, obviously the ESR resistance and the value, everything changes. So the interesting part was to find a correlation, if there was a correlation between generator and this kind of measurement, where you in fact you get the precision from the 5.5 digit multimeter, and compare with this. In fact, you do, but when you are at 10K and when I'm here at the generator at 100K. So that means for me, the measurement, even though it says 10K on the dial, is really made like a 100K measurement. So to sum it up, what we showed is that it was indeed very precise in terms of its measurements, be it resistance or high error ESR. Sorry, I don't know about the D factor. Yes, I don't know about the dissipation factor. I didn't check on that. But the one thing which is very interesting for me is that even though it's supposed to correlate, and I saw videos where they show that it's correlating to other bridges at 10K, my measurements with 100K show that it's perfect correlation when it's 100K, when this shows 10K. So this is a very good point, because in fact it means it's measuring at a higher frequency than what it says, and that's quite desirable for such a tool. And obviously the 100 Hertz, I mean the three settings make the probe quite interesting all in all. The measurements I ran between comparing between the different things, and the way I measured gave every time the same answer. You just have difference in the frequency. So overall, I'd say it's a 5-star little tool. It's obviously not the only thing you need to know about a capacitor, because I'll show that in another video, but you can measure some caps which might look a little bit wary, and will give proper numbers and ESR which are quite good and everything, but I will demonstrate in another video that this is not enough. So while this is a very nice little gadget to show ESR, it's one thing, it's not the only thing that you ought to know about the capacitor. One is also this physical shape, just like this one. It's done. And comparing the value that you have to the measurement of a capacitance is another clue whether you're okay or not. Here you see the clue is good, but that doesn't still mean the capacitor is good. In fact, it ain't good. That's for another video. I hope you enjoyed. Voila, that's for this Zoyit ZT-MD1 LCR tester. À bientôt. One more thing. Another thing you can measure is capacitance, obviously, with a scope and a generator. Here I'm generating a pulse at about 10 Hertz, and you can see here. And with the curve I can measure the 63.2%. It's here 6.328 volts. That's the between, and my timing cursor will allow me to get a value. Here it's 7.45 millisecond, which I can convert with the resistor here to capacitance using T equals RC. So this is what we'll do. I'll take my calculator and do the calculation for you. So I took off the capacitor. Here is what the meter reads, 99.19 microfarad at 100 Hertz. Okay, and the result, the calculation gave 90.85 microfarad. So, well, it's my calculation is obviously the precision is not as good here. This is the instrument that's lacking precision, but you get the feel that it's okay since it's quite in the range. I can put it back in there, up. Voila. And this is where we read the 7.45 millisecond, and I have 82 ohms here, and this is what, if you plug in the numbers, you get 90.85 microfarad. That's the result you get from that. So another way to check whether this little gizmo is giving you some proper idea. Obviously, I do have also some capacitance meter other than this, which say about the same thing. So the measures for that, for the capacitance, it's the one thing that I don't have a bridge here to check what I mean to compare the precision of this one. We can check quickly with this little multimeter, which has capacitance also, just to show what he says. And let's see what he says. This guy is a bit longer at getting an info. $104. So this is, they don't all agree exactly. 106, 107, 106.8 microfarad. That's what this one says. But it's all in the ballpark, so we're quite happy with that. The capacitance is not, anyhow you have a tolerance for your capacitors. So here this one, which is probably much closer to reality, is 99.38 microfarad at 100 hertz. Now you have to check also that the reactance is not interfering with that, namely because of the capacitance and the frequency you're testing at. Voila, that's for tonight.